Hello everyone. Today we will be discussing a research paper on transfer learning using convolutional neural network architectures for brain tumor classification from MRI images. This study focuses on using pre-trained deep learning models to classify brain tumors from MRI images. Given the limited availability of medical imaging datasets, the researchers explore transfer learning as a way to improve classification accuracy, reduce training time, and prevent overfitting. Brain tumors are life-threatening conditions, and early and accurate classification is crucial for treatment. There are over 120 types of brain and central nervous system tumors. This study focuses on three: glioma, meningioma, and pituitary tumors. Traditional classification methods require manual expert analysis using MRI scans following the WHO classification system. Automating this process can assist radiologists, reduce human error, and speed up diagnosis. Traditional machine learning approaches relies on handcrafted features and require expert knowledge. Deep learning, specifically CNNs, can automatically extract these features and improve accuracy without manual feature engineering. CNNs have been widely successful in medical imaging for detection, localization, segmentation, and classification. Training CNNs from scratch requires a large dataset and high computational power. Medical datasets are often small, making it difficult to train deep networks effectively. Transfer learning helps by using CNNs pre-trained on large datasets like ImageNet and adapting them for brain tumor classification, which allows for faster training, higher accuracy, and better generalization. So the CNN architectures used are AlexNet, GoogleNet, VGG16, VGG19, ResNet 18, ResNet 50, ResNet 101, ResNet Inception V2, and SENet for brain tumor classification problem using transfer learning. These architectures vary in depth, number of layers, and computational efficiency. CNN architectures have significantly improved over time, with classification error decreasing from 15.3% to 2.25% in SCNet. Also, the number of layers is increased from 8 layers to 152 layers. So this table basically summarizes the error rates for each of the network. So some of the key CNN networks are AlexNet, which uses 8 layers, of which 5 are convolutional and 3 are fully connected, and it uses ReLU activation and dropout for regularization. GoogleNet, which was introduced in the Inception module, improved efficiency by using different kernel sizes in parallel. It also reduces computational cost while maintaining accuracy. Thank you. Now my friend will continue from here.
Hi, hello. So my name is Vaibhav, and I'll be explaining the later half of the project. First beginning with what is transfer learning. So transfer learning is basically a deep learning technique where a model that has been pre-trained on a large data set, which is known as a source domain, is reused or fine-tuned for a new but related task known as the target domain. So instead of training a neural network from scratch, transfer learning allows us to use learned features from an existing model and apply them to a new but a different data set. So here is the example, like this is an animal of a certain kind, and we use a model and train it with this data set and use it use this knowledge to train on a different kind of animal data set rather than training from scratch. Moving on, so what a typical convolutional neural network looks like. It consists of multiple layers that learn from different levels of features. The lower layers basically are the edge detectors, which detect the edges, lines, and textures. The middle layers consist of shape detectors, which identify shapes, patterns, and object parts. And the later layers, which are higher layers, are task specific features that learn complex structures and classify objects, basically the classification part. And there are basically two strategies for transfer learning. One is feature extraction, which pretend CNN convolutional layer is frozen uh, since they capture generic image features, and they replace the fully connected layers with new layers trained on the target dataset. And this strategy is best for small data sets where retraining all layers is not feasible and a very lengthy task. And the second strategy is fine tuning, where you unfreeze some deeper layers of the CNN architecture and retrain them on a new data set, and it helps the model to learn new task specific features while leveraging patent knowledge. And this strategy is used for a larger data set where careful tuning of the learning rate is required to avoid overfitting. So coming back to the paper, so over here, instead of building a model from ground up, we use a pre-trained CNN and modify it to work on the MRI brain tumor classification. This approach is particularly beneficial in medical imaging where labeled data sets are limited. So the CNN models used over here are AlexNet, GoogleNet, VGG16, and various other architectures, total 9 of them. And this consists of 1,000 classes trained on 1.28 million training images. And these pattern models have already been learned important low-level image features such as edges, shapes, features, textures, which can be adapted to identify tumor patterns in MRI scans. So this study, like as I told, utilized 9 patent chain architectures. Each of these architectures has demonstrated higher accuracy in general image classification tasks, and their ability to process hierarchical features make them well suited for medical image analysis. The patent models take MRI image as an input and predict the tumor type along with the probability score of each category. So there are 3 categories which the architecture will be classifying. So basically 3 tumor categories, and to adapt these models to brain tumor classification, the researchers modified the last 3 layers of each network and placed them with the original fully connected layer with a new layer that outputs 3 tumor classes. So moving on, like I explained about the transfer learning, like pre-trained CNN, which is trained on a large dataset, is used to be fine-tuned on a smaller dataset to classify in 3 different classes. So moving on to experiments and results. So the study was implemented in a MATLAB 2019B on a system with Intel GPU and a 16 GB RAM. And the dataset used for training and testing was collected from 3 kind of hospitals in China, and the publicly available dataset consists of 3064 contrast enhanced MRI slices from 203 patients with the following distribution. Like we had this kind of particular disease with 708 slices, this kind of particular disease with 1400, and this kind of tumor with 930 slices. So in total we had 3000 images. The dataset was stored in MATLAB.mat format containing 2D grayscale MRI slices with a resolution of 512 into 512 pixels. Since most CNNs are designed for RGB images, the grayscale images were converted into RGB format using a color map function in MATLAB. the images were then resized based on the input requirements of different CNN architectures that we have used. Namely 227 into 227 for AlexNet and CNet, 224 into 224 for GoogleNet and VGNet and ResNet, and 299 into 299 for ResNet, Inception V2. To prepare the dataset for model training, the images were normalized to have pixel intensity between 0 and 1. And then the dataset was divided into training and testing, 60 and 40% respectively, ensuring a fair evaluation of model performance. So the model training parameters for transfer learning, the models were trained using stochastic gradient descent optimizer with a momentum of 0.9 to stabilize updates. The learning rate was set to 0.001 to allow gradual fine-tuning of the network weights, and the batch size of 120 images were used to balance memory efficiency and training speed, and this was conducted in various epochs, namely 25, 50 and 90. So to accelerate the learning in the newly added layers, the weight learning rate factor and the bias learning rate factor was increased to 10, and throughout the training process the models were validated every 50 iterations to monitor improvements and avoid overfitting. So for calculating the accuracy prediction, once the training was completed, the models were evaluated on a test dataset using classification accuracy as a primary metric. So this is a formula given for we use for accuracy metric. 2 positive plus 2 negative divided by 2 positive plus false positive plus false negative plus 2 negative into 100, and where 2 positive and 2 negative are outcomes produced when the model correctly classifies the positive class and negative class respectively, and the false positive and false negative are outcomes produced when the model incorrectly classifies the positive class and negative class respectively. So the results showed that all the CNN architectures except SCNet achieved over 90% accuracy, as you can see in this table, and the best performing model was VGG16 with accuracy of 98.71, and despite having fewer layers than deeper architectures like ResNet, and VGG16 outperformed them in this task. So another key observation was that SCNet suffered from overfitting when trained for 25 and 50 epochs, like as we can see, but its performance improved with 90 epochs, and the results also showed that AlexNet and VGG16 performed better than the deeper models like ResNet, Inception V2, possibly due to the smaller dataset size. So, and it we can also observe that the training time is increasing gradually with increase in epoch numbers, but the classification accuracy is not influenced much by the epoch number, so which means that we can consume less time using less epoch. So coming to the last part of this research paper, the conclusion and the future work. So this study presents an automated system for brain tumor classification using contrast enhanced MRI images, and this system applies transfer learning with 9 pre-trained CNN architectures, achieving high classification accuracy even with a small data set and fewer training epochs. The result shows that shallower networks perform better than deeper networks for this task, particularly due to the small data set. And for the future work, this model will be extended to classify other medical images such as X-rays, PET scans and CT scans, and Additionally, further research will explore the impact of the number of training epochs on classification performances. Thank you. This is all for the research paper.